Okay, I'm about to hit you with a lot of information here. Here we go. Colligative properties of solutions. Liquid solutions experience the following four colligative properties: vapor pressure reduction, boiling point elevation, freezing point depression, and osmotic pressure over that of their pure solvent. For example, if I just have a pure solvent, let's always think of water. If I have water in a beaker, this is what it would look like from the top view. Some of them are evaporating, therefore I have vapor pressure. But if I add a solute to the solvent, this is what the top view looks like now. Now I have all these blockers, if you will, blocking water from escaping, so therefore look what happens to my vapor pressure. It goes down. So when you add a solute to the solvent, your vapor pressure goes down. When a non-volatile, that means it doesn't evaporate, solute dissolves in a solvent, it becomes evenly distributed throughout the liquid. This means non-volatile particles are on the liquid surface. Non-volatile particles reduce the surface area from which evaporation is possible, reduces incidence of evaporation per unit area, therefore it reduces the vapor pressure, just like what I just said. Okay, Raoult's law for non-volatile solutes. The partial pressure of a solvent over a solution is equal to the vapor pressure of the pure solvent times the mole fraction of not the solute, but the solvent. Basically, this is a percentage thing. This means that the vapor pressure reduction is determined by the concentration, not the type of particles in the solution. Raoult's law for volatile solutes. Then you've got two things. You've got two things that are evaporating. The solute is evaporating, the solvent is evaporating. So you got to find the vapor pressure for the solvent, which means the mole fraction of the solvent times its vapor pressure. Pressure for the solute, which is the mole fraction of the solute times its vapor pressure. And then you add them together. And then once again, ideal solutions. Solutions act most ideal when the solute and solvent have similar structures. Intermolecular forces between the solute and the solvent are similar to those between solvent molecules. However, you can have non-ideal solutions, just like in gas laws. That occurs when intermolecular forces between the solute and solvent are strong, attracting them together, therefore the vapor pressure is lower than expected. So here I have water, and it's evaporating. And remember, vapor pressure, when vapor pressure equals atmospheric pressure, that's called boiling. That takes place at 100 degrees Celsius. If I have boiling water and then I add some solute to it, it will stop boiling. So if you add salt to boiling water, it stops boiling, okay? Because the vapor pressure goes down. That means it requires more energy, increase in temperature, for it to boil once again to get to the point where it's at atmospheric pressure. So you have to raise the temperature of the boiling water. Soluble ionic compounds completely dissociate in polar solvents. Colligative properties depend on the concentration of the solute particles in the solution. Thus, for a strong electrolyte, something that ionizes, you need to know the concentration of the ions, not necessarily the formula units. I'll explain that in just a second. So if I have a solution, it's got a boiling point elevation. When you add salt to water, its boiling point goes up. This is the equation that we can use to solve for the change in the boiling temperature. It equals something called the von Hoft factor times molality times its boiling point elevation constant. Once again, this is the change in the boiling temperature. I stands for the von Hoft factor, which is the number of ions within one formula unit. I'll show you that in just a second. M is molality, and Kb is the boiling point elevation constant for water, and I'll always give you that number. Measured values for I are usually lower than the ideal values. This tells us that the dissociated ions are not completely independent from one another. I'll explain that in just a second. Right here, for example, if I put salt in water, here's the sodium ion, positive. Here's the chloride ion, negative. Sodium, chloride, chloride, sodium. Ideally, they don't hook up together. But if we have positives and negatives, some of them are going to be attracted to another, and therefore they're going to kind of clump together a little bit. That's the non-ideal part of it. Factors affecting non-ideal behavior. Well, the higher the concentration of the solute, the more salt you pour in there, the more positives and negatives you have, the more they're going to cluster around together. Also, the greater the charge of the individual ions. If you have plus 2s and negative 2s, those are stronger charges attracting each other, it's going to cluster even more. Okay, so here we go. What is the boiling point elevation when 3.2 grams of NaCl is added to 0.65 liters of water? What is the new boiling temperature of the water? First thing we're going to do is we're going to find molality of the solution. I'm going to convert grams to moles. I'm going to divide it by my kilograms of water, and I get a molality of 0.082. That's going to be going right here. So I'm going to solve for my change in boiling temperature first. My von Hoff factor for NaCl, this breaks down into how many blockers? 2. It breaks down into Na positive and Cl negative. So I have twice the number of blockers because it's NaCl. If this was CaCl2, it would give off Ca and Cl twice. It would have a von Hoff factor of 3. So I plug in my von Hoff factor, I plug in the molality, and I plug in my constant, which I will always give you, and I get a change in boiling temperature of 0.084. So the new boiling temperature of water is not 100 anymore, but 100.084, boiling point elevation. It went up. How much NaCl in grams must be added to 0.65 liters of water to raise the boiling temperature 1 degree at ATM, 1 ATM? So I want a change in temperature of 1. My von Hoff factor is still 2. I'm going to solve for molality. 1, 2, constant, solve for molality, I get 0.98. So now that I have molality, I can plug everything else in and solve for the moles, number of moles of NaCl. I have in the molality, I have my kilograms of solvent, I can solve for my number of moles of solute, 0.64. Once I have 0.64 moles, convert it to grams, 37 grams of NaCl. So the boiling point elevates, the freezing point goes down. Freezing requires the transition from a disordered solution or a disordered solvent to a more arranged solution or solvent. So therefore it becomes more disorderly, therefore delta S is negative. Heat must be removed for the system to facilitate freezing, so delta H is negative, it's exothermic. A solution is more disordered than just the pure solvent, which means it has even more disorder, so a larger delta S. Therefore, it requires more heat to be removed. So the freezing point depression looks just like the same one. This will be the change in the freezing temperature, von Hoff, molality. This is going to be the freezing point depression constant. Like all colligative properties, freezing point depression depends on the number of solute particles. That's the von Hoff factor. How much ethylene glycol, this is antifreeze, must be added to 6 liters of water to depress the freezing point by 15 degrees. So this is going to be a change of 15 degrees. I have a von Hoff factor of 1 because this is covalent. It does not ionize into anything. So it's just one blocker. And if I plug in my 15, von Hoff factor of 1, plug in the constant for water, which I'll always give you, you'll get the molality of 8.06. If you have molality and you have the kilograms of water, you can solve for the moles of ethylene glycol. Once you have moles, you can convert to grams. All right. Here's the triple point for the pure solvent. Let's call it water, right? Even though this is not the phase diagram for water. Okay? Here's the triple point. When you add solute to the solvent, the triple point goes down. When you lower the triple point, look what just happened to the freezing point. Here's the original freezing point. Now my freezing point is over here. That's my change in freezing point. When you add solute to a solvent, the triple point lowers, and my boiling point, which was right here, is now way over here. So this is my change in boiling temperature. Osmotic pressure is the pressure needed to be added to stop osmosis from taking place. I don't know if you remember osmosis from biology, but osmosis is when you have high concentration going to low concentration. And this right here represents a semi-permeable membrane. You might have heard of that in biology. It's a filter that only allows the solvent to pass through. So if this is a solution, solute and solvent, this is just the solvent. We can think of water. Only the solvent can pass through. So this has the higher concentration of solvent. This has a lower concentration of solvent, so the solvent would be going in this direction. Osmotic pressure, which is the symbol for pi, would be the pressure that you would have to push down right here so that osmosis does not take place. So here's the osmotic pressure pushing down, forcing osmosis to not take place. Osmotic pressure is equal to I, von Hoff factor, M, molarity, R, 0.0821, and of course temperature needs to be in Kelvin. So 0.5 grams of an unknown non-acidic organic compound is this is just telling you that it has a von Hoff factor of 1, is added to a 0.85 liter of water at 25 degrees Celsius. This creates osmotic pressure of 0.0127 atms. Find the molar mass of the solute. So I have my equation here. I have my osmotic pressure right here. I've got my molarity, or at least I can solve for molarity. I've got my von Hoff factor. R is 0.0821, temperature, and now I solve for molarity. Once I have molarity, I can solve for the number of moles. If I have 0.85 liters and it has a molarity of this, that's how many moles of solute I have. To find the molar mass, remember molar mass is always grams divided by moles. So I take my 0.15 grams of solute divided by the moles, 340 grams per mole.